Hello. In this video, we'll continue learning about how we can perform motion analysis in Creo. In the previous video, we learned how we can perform kinematic analysis, which requires us to prescribe details about motion, and we do that by prescribing different types of servo motors. And kinematic analysis is a form of analysis in mechanics in which we don't worry about the forces acting on the mechanisms that we're looking at. If we start worrying about the forces, those kinds of analysis are known as dynamic analysis, and that is the kind of analysis that we'll be performing mainly in this video. But there is this intermediate analysis category that Creo offers, known as static analysis. In static analysis, we do account for body forces like friction and gravitational forces, but the goal over here is not to study the details of the motion of a body in response to different forces. It's just to determine what would be the equilibrium position under the action of those forces that the body would arrive at. So we don't study how the body would get to that stage. For example, if we have a reciprocating pendulum, it's dropped from this point. We won't worry about whether the pendulum would go beyond its equilibrium position, then come back, and eventually, as energy is dissipated, settle at its equilibrium position in static analysis. That's something that we will and can do in dynamic analysis. Static analysis will just tell us that a body with such a mass distribution being acted upon by gravity will eventually come to this resting state. And that in some cases is useful. So we'll very quickly take a look at that. And then we'll move on to dynamic analysis. And as we just said, dynamic analysis takes a look at the complete picture. And that's why it's more computationally expensive as well. If you're not certain whether you want to perform static analysis or kinematic or dynamic analysis, you can go with dynamic analysis as long as you are willing to pay the computational price. For example, if we have this pendulum and you drop it from here, it might take 30 seconds to eventually come to an equilibrium state. That means that you'll have to run your dynamic analysis, which is computationally demanding, for at least 30 seconds, for 30 seconds in real time. That might mean that in actual computational time, depending on your processing power, it would have to be run for for a significant amount of time. Whereas for static analysis, it's almost instantaneous, where Creo calculates what is the final position of the body. And unlike kinematic analysis, both for static and dynamic analysis, we need to prescribe the mass of our body, which is something that we haven't done previously, because when we're talking about forces, the magnitude of a force, if we know the acceleration, can be calculated if we know the mass of the body, F is equal to ma. So we need to prescribe the mass, which is a measure of the body's momentum and inertia, before we can carry out static and dynamic analysis. And if we want to study the effect of gravitational acceleration, then we need to define a gravitational field as well. So that's what we'll learn today. Let's get started. I have Creo opened up over here. This is my base assembly, which I have base part, which I have added to an assembly on which I'll add additional parts which will be movable, and we'll use that to perform static and dynamic analysis. One thing to make sure is that the first part that you have, that should not be movable. So as we've discussed previously, the constraint that we use for the first immovable entity that we have in our assembly is of the default kind, which fully constrains the part. So if I were to grab it using the drag component tool, it wouldn't move. I've made a simple link that I'll use to make a compound pendulum. I'll import that link over here, and I'll assemble that on one of these shafts using a pin joint. We know how to define a pin joint. We define the axis of rotation. Then we then we fix the translation distance. I'll have it be somewhere over here. And if you wanted to, you could constrain the degrees of rotation as well by prescribing additional constraints. For some reason, it did not define this translation position as I wanted it to. So hopefully it's correct now. And we want it to be fully moving, so we can leave it as is over here. But as I'll show you later, there is a reason why we do need to define two planes, two reference planes, if we are carrying out dynamic or static analysis, or sorry, dynamic analysis, because within this option where we are defining the rotational axis is where we can prescribe properties about friction. We'll come back to that later, but for now, just select a plane on your part and a plane on your assembly. And what we could do if we wanted was to set this as our zero position, for example, and then use that as a minimum limit. And if we only wanted to allow movement within a certain number of degrees, then we could have prescribed the maximum limit as well. But we will not do that, which means our part can move an entire 360 degrees. So we have a link over here. And as I said previously, we want our part to have some mass. So we need to prescribe a material. If we go to analysis and we select measure, and if we select a part, it tells us what the area of the part is and what the volume of the part is. Right now it's talking about the base plate. We can do the same for the link as well. And this we can hopefully understand how Creo can compute, because it knows how many surfaces there are. From that, it can calculate the total surface area, and it knows the depth and all the dimensions in 3D. And from that, it can calculate its volume. And very simply, for it to calculate the mass of this component, it needs the density. Density is the mass per unit volume. And we can either go to the settings of that part and manually enter the density, which would be in the units of kilogram per meter cube or similar units in different systems of unit. Or we could tell Creo that I want this part to be, for example, made of steel. And then from its own database, Creo will pull what density of steel is, use that with the volume of that part, and then it will tell you what the mass of your part is. To define the mass, define the material of an individual part, you need to go to that part. So I'll open this part, which I'm calling as link, and by default, a material is not defined. To define a material, you have to go to prepare model properties. This is the same menu where we can go and change the system of units, model properties. And over here, in this case, I have defined a material, but I'll show you how to do it again. But by default, a material would not be assigned. So where it says material, go to change, and you'll get this menu. And from here, select a material that you want. You can play around with this library. This is the standard library of materials that Creo has, and for most applications that's good enough. I want to have the material be made out of a plastic. Let's say I want it to be made out of ABS, which is actually a material that we can 3D print, not using the 3D printers that we have, but we can using some of the more advanced 3D printers. It also has PLA. So if you wanted to calculate the mass of something that you're 3D printing in PLA, assuming you know the infill density, or the infill density is 100%, you could select PLA, and it should give you a reasonable estimate of what the weight, the mass of your body will be when it's printed. So let's select PLA. I've selected PLA. So this is actually not assigned. double click PLA. Now it should be selected. I click OK, and the bead material is not changing. Let me. Okay, so you have to select it from here as well. Okay, and let me. Okay, so when I right click it, set as master, if I've selected multiple materials, then that material is selected and it's assigned to your part. If you did not know what, if you did not find the material that you wanted in Creo's library, you could go over here and define the density of your part over here yourself, and for most applications that might be good enough. So if you don't want to don't know exactly the density of don't have the exact type of steel in Creo's library that you're working on, you can calculate it, its density experimentally, and then define that over here. And if you want to know what the mass of your body is, you will go to analysis and you can look at mass properties. When you select mass properties, this table opens up. Uh, Click preview, and over here it will tell you that this body has a mass of 10 to the power minus 2, which means 10 grams. All right, so this is how you can assign a material and then measure its mass. If you are interested in finding out where the center of gravity of your part is, uh, Creo shows you that as well by this coordinate axis, where you have the 1, 2, 3 labels, and over here it also tells you what are the coordinates of the body's center of gravity with respect to the part's original coordinate system x, y, z. And in many analyses, you might need to know where the center of gravity is. For example, if you want to balance something, you want the center of gravity to be at a particular position. So this is how you can determine the center of gravity. Of course, Creo does assume that the mass within that part is distributed evenly. So if there are any heterogeneities, there are any imperfections, those would not be accounted for explicitly in Creo. This is how you can define a material for a part. And now this part has some mass. So now we'll try to perform static analysis on this part. So open up the mechanism application, and we'll define a new analysis. You can define a new analysis from here, or you can left click over here and click new over here, which allows you to define a new analysis. I'll call it my static analysis, and the analysis type has to be selected from here. I'll select static, and you have to give it an initial position. Generally, I don't like using this option where the initial position is prescribed by the orientation, but for now I'll let it slide. But a better idea is to take a snapshot, as we'll do for the dynamic analysis. Click OK. One thing that we need to do, what I want to look at, is that if I were to let this part drop from this position, where would it land under the action of gravity? We haven't told Creo what is the gravitational acceleration. It would be what we have read in our textbooks, because we are on Earth, and if you're not being very sensitive about changes in altitude, 9.8 meter per second squared is acceptable. But we also have to tell Creo what is the direction. We know that it's vertically down, but Creo doesn't know if this is vertically down or this is vertically down. So for any analysis where you want the influence of gravity to be included, define gravity from here. There is a vector that is pointing to the direction of gravity right now. We don't want gravity to be in this direction, which is minus y. We want it to be in this direction, which I think is positive z. So we want gravity to act in this direction, and this is the right value, 9.8 meters per second square in millimeters, of course. This is how you define gravity. And now if I go to my analysis, I click run. What I will expect, what I was expecting was that it would drop to its equilibrium position, but it did not do that. And that's why, because even though we have defined gravity, we haven't told this analysis that we want you to take gravity into account. If you want to do that, then you have to go over here and enable gravity. Once I've enabled gravity, now Creo, while analyzing the motion of this part, will include the effect of the gravitational field. And now when I hit run, it drops to what should be its natural position under the action of gravity. Let's look at it perpendicularly. So this is what you would have expected, that you have something in a non-equilibrium position under the action of gravity. It would eventually come to this position. We know from experience that it wouldn't have just dropped to this position. It would have oscillated and then eventually settled down to this position. That's something that we can study using dynamic analysis, and we look at that next. So the results from static analysis only tell us what the natural equilibrium position of a part is. Don't use that as any indication of how long the part would take to get to this position. So now let's start a new analysis. I'll make a new analysis over here. I'll call it my dynamic analysis. And I wanted to run for 15 seconds. Frame rate set according to your needs. If you increase the frame rate, you'll get better details, more resolution, temporal resolution, but it would slow things down. For now, I'll keep it at 10, but if this is something that I was reporting somewhere and was the final analysis of my project, I would use a frame rate closer to 100 frames per second. For dynamic analysis, you do need to define the initial configuration or the initial settings, initial conditions for your model, and for that we need to take a screenshot, a snapshot. So let's have the part be at a slight angle from the vertical, and take a snapshot. Call it almost vertical. I don't know why they can rename it. Okay, forget about that. Almost vertical, so I have that position set. Now I can move this part wherever I want, and I can tell my analysis to start from that particular position that I just defined. So the initial configuration in my dynamic analysis would be the snapshot that I just took. But in dynamic analysis, you need to set up what's known as not an initial state, but an initial configuration. And for that, in addition to a screenshot, you can define additional initial conditions as well. Let me show you where you can do that. So over here is where you can define different initial conditions. This is an initial condition that I'm using. The original position that I want it to have this position of the snapshot. In this particular case, I don't care what the initial velocity is, but if you wanted to, you could provide other additional initial conditions as well, where, for example, you could tell Creo that at the start, well, this button is for defining velocity of a point. You can select a point on your model and tell Creo that initially I want this point to have a velocity of 2 meters per second. Then when Creo starts its analysis, this link would not be stationary. It would be moving, and then Creo would take that into account while calculating all of the forces. But over here, we'll keep it simple. We don't want to define any velocity initial conditions. We just want the analysis to start from this orientation. So I'll select OK over here, and I have defined my initial condition, which I'll link over here in the initial configuration. Right now, we only have one initial configuration. You might be interested in analyzing a problem with different initial orientations and different initial velocities, so you can set up multiple initial configurations. You can add motors to your dynamic analysis as well. We don't want those, and we do want gravity to be included. So we'll select gravity from here. And now when I run this analysis, Creo starts from that initial position, and the part drops under the influence of gravity, and it oscillates as we would expect from a compound pendulum. And one thing that you might be noticing is that its oscillation, the amplitude is not decreasing, which is something that we would expect in real life. And that is because in real life, we have energy being dissipated through friction. And over here, we haven't enabled friction, which is because we haven't defined friction. And because of that, what happened was that in our analysis ran for 15 seconds. And during those 15 seconds, the part oscillated continuously. And if we were to run this analysis for a hundred or 1,000 seconds, we would still have an oscillating pendulum at the end, which is unrealistic, but it's correct as per the laws of laws of mechanics. Because if you don't have friction, you have to conserve energy, and the pendulum would continue oscillating indefinitely. We'll fix that, but before we do that, let's see how the position of this part changed. We know how to define measures, so we'll go to measure and define a new measure on this point. And I am interested in, for now, seeing how the magnitude of the position of my part changes. What might be actually more interesting is how the head component, which is the vertical component, how that changes with time. So I'll define this measure, and I'm interested in the results of the dynamic analysis, and I'll plot that. And these are the results that you get. Initially, the part dropped from a height, its position landed to this level, and after that it started its oscillatory behavior, and it repeated itself every cycle. And something that you notice is that it's not coming to a halt because there is no friction. So let's rerun this analysis, but now with some friction added. You can do this in mechanism, but let's exit from mechanism and do it in our normal assembly tab, because it's something that you should do while you're assembling your part. On my pin joint, I will define friction. So, and this is why we selected two reference plane to potentially limit our pin joint rotational freedom, but we did not select any limit here. We did not limit that, but we can now define dynamic properties, which include friction. To define friction, you need to prescribe three things. You need to prescribe the coefficient of static friction, which all of you should know from your courses in physics, the coefficient of kinetic friction, and the radius of contact. I'll tell you what that is, but let's start defining things. So let's say that My coefficient of static friction is zero point 0.4. My coefficient of kinetic friction, I can choose zero point 0.2 because kinetic friction is usually smaller than dynamic friction. In your projects, if you are choosing these values, you'll have to justify those, that for this material, according to this database, the usual coefficients of friction are the following. And the radius is the radius of contact of your pin joint. So in this case, I know that the diameter of this shaft is 10 mm, so the radius of contact would be 5 mm. That is needed to determine the area of contact along which there would be friction. So I've prescribed dynamic properties, which are properties of friction in this particular case, and I've enabled friction from here. So now, if I open mechanism and I rerun my dynamic analysis, but this time around, okay, I did not save that. Dynamic analysis, initial state, I'm running it for 15 seconds. I'm not only enabling gravity, I'm also enabling friction. Let's see what happens. It starts from the same position, and you might be noticing that it is now coming to a stop. By the way, this bar over here tells you how much of that total runtime, which was 15 seconds, has been concluded. And now when we plot the results, we should see something different. Here you can look at the coordinate system and make sense of what these values mean. Just from first glance, what I can see is that it's oscillating with a particular amplitude, but then with time that amplitude is decreasing, and eventually it comes to its resting position, which is the distance of that point from the reference coordinate system in the z direction. You could modify your measures to look at the other components as well. Let's look at the y component. What would you expect that to be doing? I would not expect that to do anything because nothing is changing the in the y direction, but let's confirm that in the y direction nothing changes. What about the x direction? Things should change in the x direction. So now if I look at the x component, I see some periodic behavior again, which eventually comes to a halt. Play around with the different values of friction. If you increase friction, what should happen? You would expect that things would come to a halt quicker because you're dissipating energy faster, but explore that on your own. And you have an assignment associated with this topic in which you have to add a second linkage to the end of this pendulum and then repeat this exercise. And you should use the same link that you make for a second time in assembly. Pull the whole thing up, drop it, and set up your dynamic analysis such that your assembly eventually comes to a halt. So set up friction parameters accordingly. They should be realistic as well for the materials that you've selected, and set up your duration of analysis accordingly. So this is how we can perform static and dynamic analysis. We use the example of a pin joint, but you can also do that for slider connections. We don't have a piston right now, but if you wanted to see what would happen to a piston under the action of gravity or under the action of different forces, you could do that as well. One thing that I'll very quickly show is that how you can define different forces. So let's say that you wanted a force or a torque to be acting on this link. You could define that from here. You could either use a force motor, or you could use this option which defines forces directly. I'll select this body. This is where I want a torque to be acting because it's a pin joint. We will define a torque, and the vector representation of a torque is perpendicular to the plane of the moving part. So we want the part to be rotating in this plane, so the vector should be pointing into the board. So that should be in this direction. And similar to how we've done previously, you can give it a constant value, or you could use a different kind of a function, and then that force would act for that period. I'll give it some value, click OK, and if I were to go back to my dynamic analysis, I could add that force over here. That's the only thing that I've defined. So yeah, in that way you could define forces explicitly. Explore this dynamic analysis menu on your own, and thank you for watching the video.